Picture this. You're sitting in a doctor's office, right? The physician walks in, glances at a piece of paper, and tells you your test results are positive. In that split second, your heart just drops. Naturally, you implicitly trust that result. I mean, why wouldn't you? But actually, should you? You see, medical tests aren't magic crystal balls, they're statistical tools. And today in this explainer, we're actually diagnosing the diagnosis itself. We're going to uncover the hidden math behind medical trust, and by the end of this, I promise you, you will literally never look at a lab result the exact same way again.
Okay, so here's our roadmap for today. First, trusting your medical tests. Then, we'll dive into the confusion matrix, followed by calculating the scores, and finally, we'll wrap up with real-world diagnostic stakes.
All right, let's jump right into section 1, trusting your medical tests.
So clinical decisions carry incredibly high stakes. Whether it's an optometrist checking your vision or an oncologist screening for cancer, the statistical metrics we're about to explore influence literally every single decision a doctor makes. So seriously, ask yourself, how much confidence do you actually have in your medical tests? Let's take a real-life example from eye care. Imagine an eye doctor is trying to diagnose glaucoma, which, is a serious condition that can lead to blindness. What if they relied on just one single measure, like intraocular pressure, or IOP? Well, as our source material points out, measuring pressure alone has terrible reliability for detecting glaucoma all by itself. You absolutely have to look at other factors, like the optic nerves and visual fields. Relying on a weak test? That means you might have zero confidence in the result. So how do we actually measure that confidence?
Well, that brings us to our first hero metric, sensitivity. By definition, sensitivity is a measure of how often a test correctly detects a positive result. You can kind of think of it as the test's ability to catch the bad guy. If someone truly has a disease, how sensitive is the test to actually finding it? Like, for example, how often does measuring blood sugar correctly catch a true case of diabetes? Or, if we use that eye pressure test, how often would we correctly diagnose an actual case of glaucoma? Basically, a high sensitivity means very, very few sick people are slipping through the cracks.
But here's the thing, catching the disease is really only half the battle. We have to immediately contrast this with our second hero metric, which is specificity. Specificity represents how often a negative result from a test correctly determines that a person does not have the disease. So if we only used eye pressure, how many completely healthy people would be correctly told, hey, you're fine, you don't have glaucoma? Specificity is the metric that gives healthy patients peace of mind. And it's absolutely crucial because it keeps us from over-treating people who just don't need it.
Moving right along to section 2, the confusion matrix. Okay, now that we've got our 2 hero metrics down, we need a mathematical framework to actually track them. Enter the confusion matrix. We're going to treat this matrix exactly like a visual puzzle. Let's start deconstructing this step by step, starting right at the top. Notice the columns labeled true condition. This represents absolute reality, what the patient actually has. And how do we know this true condition? Well, doctors use what are called gold standards, or they use long-term patient monitoring. A positive here means they definitely have the disease. A negative means they definitively do not. This is pure reality.
But what's really interesting here is the predicted condition along the rows on the left. This is what the medical test just guessed about the disease. This is that piece of paper your doctor hands you. The test predicts either positive or negative. But as we're about to see, the test prediction doesn't always match up with the patient's true reality.
And when the test gets it wrong, well, that's when we enter the terrifying life-or-death stakes of diagnostic errors. Look at this stark contrast. On one side, we have a false positive. That's telling a perfectly healthy patient they have glaucoma when they actually don't. That causes immense emotional trauma, panic, and potentially dangerous, completely unnecessary treatments. On the flip side, we have a false negative, telling a sick patient they do not have glaucoma when they actually do. And that is a severe medical danger, because that patient goes home thinking they're totally fine, while their disease just quietly progresses.
Fortunately, though, tests usually do get it right. I want to guide your eye to the top left quadrant, the true positives. In this specific studies matrix, the system successfully and correctly identified 102 people who actually have the disease. The test said positive, and the reality was positive. This is exactly what we want our medical tests doing.
And if we slide diagonally down to the bottom right, we find the true negative quadrant. Here we see 124 people correctly diagnosed as not having the disease. The test said negative, and reality was negative. These are the folks who get to go home with total peace of mind.
All right, section 3, calculating the scores.
So we've seen the raw numbers in our visual puzzle.
Now, let's shift focus and see how these individual quadrants are combined to actually calculate our overarching confidence levels. Let's walk through the math real quick. To find sensitivity, we take those 102 true positives, and we divide them by all 119 people who actually had the disease. That gives us an 86% sensitivity. Not bad at all. Now for specificity. We take the 124 true negatives and divide them by all 134 people who are actually healthy. That gives us a 93% specificity. And boom, just by organizing the data, we now know exactly how much to trust this test.
Finally, Section 4, Real-World Diagnostic Stakes. Let's pivot from all this abstract theory to a tangible, real-world clinical setting. Here we have a modern TopCon diagnostic camera sitting right next to an intricate, highly detailed fundus photograph of a retina. We're looking at advanced tools used to detect diabetic retinopathy, which is a diabetes complication that affects the eyes. Recently, researchers actually evaluated an intelligent, photograph-based diagnostic technology to see if a computer could accurately diagnose this condition.
And I really want to emphasize this incredible number, 97%. In a massive 500-patient study, this intelligent diagnostic technology achieved a 97% sensitivity for detecting diabetic retinopathy. Think about that. That means out of all the patients who actually had the disease, the computer correctly flagged 97% of them. That is an incredibly powerful safety net.
And this evaluation table brilliantly illustrates the true success of the technology. While achieving that massive 97% sensitivity, the system successfully maintained a 95% specificity. Remember, specificity is clearing the healthy people. This means the computer isn't just wildly guessing positive for everyone just to inflate its sensitivity score. It's highly accurate at identifying healthy eyes, too, resulting in very, very few false alarms.
To track this balance, researchers use what's called an ROC curve. It plots sensitivity on the vertical axis against 1 minus specificity on the horizontal axis. This curve is basically the ultimate visual tool used across tons of studies to chart the balancing act between catching diseases and avoiding false positives. A perfect test would shoot straight up to the top left corner, so the closer the curve bows toward that top left, the better the test is.
So the crucial point here is that medical testing is fundamentally a very delicate trade-off. It's a game of tug of war. Ideally, sure, we want high scores for both sensitivity and specificity, but even high numbers might not be enough. If you're screening for a highly fatal disease, missing even one single case is critical, so doctors might actually accept more false positives just to make sure they catch every single actual case. They constantly have to balance the severe harm of missing a critical illness against the immense panic and cost of misdiagnosing a healthy person.
So we've unpacked the confusion matrix, we've calculated the metrics, and we've seen how intelligent technology balances this high-stakes tightrope. It really changes how you view the entire medical landscape, doesn't it? So I'll leave you with this. Knowing the hidden math, the trade-offs, and the sheer statistical weight of the confusion matrix. The next time a doctor hands you a piece of paper, will you ever look at a positive test result the exact same way again? Keep questioning, keep learning, and as always, thank you so much for joining me on this explainer.